The invisible circuit, how your body powers your phone's touchscreen. We live in an era defined by touch. Tens of thousands of times a day, your finger meets glass. You swipe to unlock, pinch to zoom, tap to type, and gesture to navigate. It feels unbelievably natural, instantaneous, and direct. It feels like you are physically pushing buttons on a screen, but there are no buttons. Have you ever genuinely stopped to wonder how a cold, inert piece of glass knows exactly what you want to do the instant you want to do it? The most common assumption is simple, intuitive, and completely wrong. Most people believe the screen feels the pressure of your finger. That is a myth born from obsolete technology. Modern smartphones do not feel pressure. They feel you. Welcome to the hidden, invisible physics of the capacitive touchscreen. To understand the present, we must briefly understand the past. The idea that screens react to pressure comes from older technology called resistive touchscreens. Think back to early PDAs, old Nintendo DS handhelds, or the clunky screens on ATMs from a decade ago. Those screens felt soft and slightly squishy. They worked mechanically. They consisted of two flexible plastic sheets coated with resistive material, separated by a microscopic air gap filled with tiny spacer dots. When you press down with your fingernail or a stylus, you physically deformed the top sheet, forcing it to touch the bottom sheet. This completed a simple electrical circuit at that specific point. The system measured the resistance change to calculate the location. It was crude. It required physical force. The plastic layers degraded the image quality, and crucially, it could only register one touch at a time. Multi-touch gestures like pinch to zoom were physically impossible. Your modern smartphone is an entirely different beast. It is a solid-state device. There are no moving parts. There are no air gaps. There is no physical compression happening whatsoever when you tap an app icon. Instead of relying on mechanics, your phone relies on pure electricity and quantum physics. To understand how this works, we need to grasp two fundamental concepts that might seem unrelated. First, your phone screen is not just a piece of glass. Second, and most importantly, your human body is an electrical component. Let's dissect the anatomy of the screen first. What you touch is just the protective top layer, usually a chemically strengthened material like Gorilla Glass. It has zero electrical function other than protection. But immediately beneath that glass lies the real magic. There is a virtually invisible grid of transparent electrodes. This material is a technological marvel called indium tin oxide, or ITO for short. ITO is a rare ceramic material that has a unique combination of properties. It is highly conductive to electricity, yet it is almost perfectly transparent to visible light. Your phone manufacturer paints this ITO into an incredibly fine grid of thousands of microscopic rows and columns across the entire display area. Think of it like a relentless, invisible game of battleship playing out just under the glass. This ITO grid is an active electrical field. The phone's processor constantly pumps a tiny, regulated electrical current into this grid. This creates a uniform, stable electrostatic field across the entire surface of the screen. Imagine a perfectly calm, perfectly flat surface of water in a swimming pool. The phone's controller chip is like a lifeguard, constantly monitoring this surface, looking for the slightest ripple. Right now, with no fingers on the screen, the charge across the grid is stable and uniform. In physics terms, every intersection point on that grid has a set, baseline capacitance. Capacitance is simply the ability of a system to store an electrical charge. The screen is holding its breath, waiting for something to disturb it. Now, enter the human element. This is where you become part of the machine. Your body is not an insulator. You are an electrical conductor. You are essentially a walking, talking sack of salt water, full of dissolved electrolytes like sodium, potassium, and chloride. Because of this chemical makeup, your body is capable of holding and conducting an electrical charge. We are vast reservoirs of mobile electrons. When your finger approaches the glass surface of your phone, you don't even have to physically touch it. Just getting very, very close is enough. Your finger enters that uniform electrostatic field generated by the ITO grid. Because your body is conductive and has a different electrical potential than the screen, your finger acts like a sponge for electricity. It steals, or siphons, a tiny fraction of the charge from the grid at that specific point of near contact. The electrical current that was happily flowing through the ITO rows and columns suddenly finds an easier, alternative path out of the grid and into your finger, and by extension, into the vast capacitance of your entire body. This doesn't shock you because the current is incredibly minuscule, measured in microamps, but it is more than enough for the phone's sensitive electronics to notice. This event causes a sudden drop in charge, a change in capacitance, at specific intersections of the row and column electrodes. Going back to our water analogy, your finger is like a stone dropping into that calm swimming pool. It creates an electrical ripple that spreads out from the point of impact. Hidden deep inside the phone's logic board is a dedicated touch controller chip. This chip's entire existence is dedicated to watching that ITO grid. It scans the state of every single intersection on the grid thousands of times per second. It is constantly asking, is the capacitance stable at coordinates 10, 50? How about at 10, 51? When your finger steals charge, the controller notices a sharp voltage dip. For example, it sees a dip at the intersection of row 45 and column 112. It instantly calculates the center point of that electrical disturbance and sends those precise X, Y coordinates to the main operating system, iOS or Android. The OS interprets that X, Y coordinate. It looks at what is currently displayed at that location on the screen. It thinks, the user just tapped the area occupied by the camera app icon. It then launches the camera app. This entire complex chain of events, from your finger disturbing the electrostatic field, to the controller detecting the capacitance change, to the OS processing the coordinate and launching the app, happens in mere milliseconds. It is so fast that to your brain, it feels instantaneous. This fundamental mechanism of capacitive sensing explains every quirk, feature, and limitation of using a modern phone. Let's walk through them. First, why does multi-touch work? Because the controller chip is powerful enough to detect dozens of separate voltage dips simultaneously across the vast grid. If you put two fingers down to zoom in on a map, the controller sees two distinct centers of capacitance change. It tracks the distance between them. As you move your fingers apart, it tells the OS that the distance between the two touch points is increasing, and the OS translates that into a zoom in command. This was the revolutionary breakthrough that made modern smartphone interfaces possible. Second, why don't your fingernails, a regular plastic stylus, or your car keys work? Because fingernails, plastic, and metal keys are insulators, or at least not connected to a large capacitor like your body. They cannot conduct electricity effectively. When you touch the screen with your fingernail, it cannot steal charge from the ITO grid. You are poking the screen physically, but electrically, you are invisible. The electrostatic field remains undisturbed. The phone literally does not know you are there. It's not ignoring you. It cannot sense you. Third, why does water make your screen go crazy? Have you ever tried to use your phone in the rain or with sweaty hands after a workout? The screen glitches out. It scrolls wildly, registers phantom taps you didn't make, or refuses to respond to your actual touch. This is because water, especially tap water, rainwater, or salty sweat, is also conductive. A droplet of water sitting on the screen acts just like your finger electrically. It sits on the glass, bridges several ITO electrodes, and changes the capacitance at that location. The touch controller gets incredibly confused. It sees 10 or 20 fingers touching the screen at once where the water droplets are. It can't distinguish between your actual finger and a raindrop. It gets overwhelmed with noisy data and fails. This is why waterproof phones still struggle to work when the screen is actually wet. Fourth, why do thick screen protectors cause problems? Remember, the electrostatic field projects slightly above the surface of the phone's actual glass. It's an aura. If you put a thick layer of additional glass or plastic on top, you are physically moving your finger further away from the ITO grid beneath. Capacitance drops off sharply with distance. If the protector is too thick, your finger might not be able to get close enough to disturb the field effectively. The signal becomes weak and unreliable. This results in missed taps, a feeling of lag, or a general loss of sensitivity. High-quality screen protectors are painstakingly engineered to be thin enough and have a dielectric constant that allows the field to pass through them without too much degradation. Finally, how do touchscreen gloves work? In winter, regular wool, cotton, or leather gloves act as insulators. They block your body's electricity from reaching the screen, just like your fingernail does. To use your phone in the cold, you need special touchscreen gloves. They are not magic. If you look closely at the fingertips of these gloves, you will see silvery or gray threads woven into the fabric. This is conductive thread, usually made by coating nylon with silver or copper. These conductive threads create an electrical bridge. They connect your conductive finger inside the glove, through the insulating fabric barrier, to the surface of the screen outside. They extend your body's electrical presence. When you touch the screen with the glove, the charge travels from the grid, through the conductive thread, and into your body, completing the invisible circuit just as if you were touching it directly. In conclusion, the capacitive touchscreen is a brilliant example of invisible engineering that we take for granted every second of every day. It turned the human body from a passive user into a necessary, active component of our device's electrical circuitry. We are no longer just pushing mechanical buttons on a machine. We are closing circuits with our very biology. The next time you effortlessly swipe through a photo album or type out a text message, remember that you are not physically moving anything on that screen. You are conducting an invisible orchestra of electrons, dancing across a microscopic grid of transparent wires, thousands upon thousands of times per second. You are the power source that makes the magic happen.